In 2005, I was a project manager in Kabul, Afghanistan. And every few weeks, I would take Henry, our CEO, for a walk around the construction site. Even though we had 63 people on that site, it rarely looked like we were actually doing anything. And I remember that through each one of those meetings. 5 years later, in 2005, I was a PhD student looking, in 2010, I was a PhD student looking for a topic. And I found myself in Amsterdam, the Netherlands, on a construction site, in a meeting that was about 6 weeks of structural steel delay. Each day was going to cost 50,000 euros. And the 2 million euros of penalties and counting made it a very heated meeting. During the meeting, I got up, looked outside the office window, and I saw 6 people occupying an area the size of a football field. At that moment, I knew that I had my topic. So, space and time are two fundamental dimensions of human comprehension. And we are all intimately familiar in our daily lives between the correlation of space usage and time. What the guiding principle of this research is to study the correlation between construction site space and construction site time. This research was motivated by 2 observations. The first observation is that there are actually millions of ways to schedule a given construction project. The large number of scheduling possibilities is a consequence of variables such as sequence. A simple example is taking a look at 9 columns. You have 9 choices to install the first column, 8 for the second, 7 for the third. There's actually 9 factorial or 362,000 ways to install 9 columns, sequences. Another such variable is labor capacity. Think of a construction manager considering up to 5 carpenter crews, up to 5 masons, up to 5 rebar crews, or up to 5 MEP crews. That's a total of 625 resource capacity configurations that the manager needs to consider. And these are not the only 2 variables. I've introduced construction sequence and labor capacity. Another such variable is schedule execution, and more precisely, what I'm interested in are delays. When you delay a construction project, you poorly execute it halfway through, that changes the ranges of metrics that are available to you in the future. And another variable I'll be looking at is the construction scheduling method. Each method models constraints differently and therefore has different limitations. And I will show you the limitations of current tools today in this presentation. The second observation is that construction sites are empty. I've worked in construction projects across 3 continents, and I can assure you that almost all of them look something like that. I invite all of you to look at the next construction site you see and count how many people you see on a site. Think of how much extra work you could be doing at this given time. To validate this observation, I performed an experiment on the IRDito project in the Netherlands, where I split the project into 403 zones, each one roughly the size of this room. I found that on average, 3% of these zones were being used for construction. I repeated this experiment on the bioengineering, chemical engineering project next door, where I took a photograph of 18 bays every 21 minutes and counted which of these bays had people inside of them. And I found again that roughly 3% of the space was being used for construction. These are 2 projects 10,000 miles apart, and these numbers were consistent across times of the day and days of the week. 3% is an extremely low number. It's extremely low. And this really tells you that construction scheduling methods need to maximize space utilization, therefore shortening construction duration. Empty construction sites point to a significant potential to schedule more processes concurrently, increasing space utilization and reducing construction duration. But you can't simply increase space utilization by just cramming a lot of people onto a construction site. That leads to spatial clashes. An example of a spatial clash is if you have a construction layout like this one, and you schedule process A and process B at the same time, it leads to a spatial clash, which reduces safety, quality, and productivity, and is thereby undesirable. I validated this correlation between overuse and reduce productivity on the Accessorize project, where a project that had a duration of 4 weeks was forced by Schiphol Airport, the airport in Amsterdam, to a duration of 2 weeks. This was a hard deadline. This area would turn airside, and to access it, you need a plane ticket. This resulted in 61 spatial clashes that I measured on the construction site, which caused 18% of the total labor hours to be lost. This shows you that construction scheduling methods need to eliminate spatial clashes. So you need to maximize space utilization while eliminating spatial clashes. Clearly, there's a trade-off between space utilization and construction duration. So how do construction managers find that right level of space usage amongst the millions of possibilities, scheduling possibilities that exist? Well, today, they create a single schedule using the critical path method or the line of balance method. This is inefficient, and I will later in the presentation show you why. Imagine that you create a single construction schedule represented by this dot here. Even when you draw the axes of construction duration and space usage, my question to you is, how good is this schedule? How close to the limits, or how fast is it compared to other schedules for this construction project? Other fields understand the trade-off between two metrics by drawing an efficiency frontier that visualizes the sets of efficient, inefficient, and infeasible solutions. In finance, you correlate risk and expected profit. In energy analysis, they correlate energy consumption and level of service. And in healthcare, they correlate the number of nurses and dialysis machines to the number of patients treated. So I started to get interested in whether you could do this for construction. And if you could, then this line would represent the fastest a construction project could be built for a given level of space usage, which is, I would call it, the operational efficiency frontier. The research question that I'm presenting here is, what is a method for construction managers to visualize the scheduling state space by demarcating the sets of infeasible, efficient, and inefficient scheduling solutions? Once you have this frontier, you still need the schedules. You need to go out there and build it. So what you really want to know is, which of these variables that I introduced can you change to navigate the state space by automatically generating thousands of feasible schedules? And the research question is, what is a method that enables construction managers to navigate the state space by automatically generating multiple feasible schedules? Once you've generated these schedules, what you want to do is you want the ability to manipulate the efficiency frontier with these variables and move it to a new location, thereby enabling more efficient solutions for your construction project. And the research question is, what is a method that construction managers can use to manipulate the sets of infeasible, efficient, and inefficient solutions? To recapitulate, the first research question is, how can we draw the operational efficiency frontier that divides the state space into efficient, inefficient, and infeasible solutions? The second question is, how can we move that frontier? Which variables allow you to move that frontier? And the third research question is, what is a method that enables construction managers to automatically generate construction schedules? So the big idea theoretically is, how can you model space as an asset that enables understanding the limit of the trade-off between construction space and time? From a practical perspective, what you want to do is, you want to be, if you understand this limit, you can then move it, thereby enabling faster construction schedules. So I'll start with my first contribution, an automated scheduler called the tri-constraint method. And before I introduce the tri-constraint method, let me tell you about what construction schedulers need to do, be they human or algorithmic. At the very least, construction schedulers need to create feasible schedules. To do that, they must satisfy functional requirements. You cannot exceed the available labor, you should not schedule crews in the same space, and you need to satisfy the laws of physics. The mechanism that guarantees that you do not violate these functional requirements is called the constraint. The constraints that model these three requirements are discrete, disjunctive, and precedence. And what distinguishes these constraints from each other, and this is a critical point, is the types of resources that they model. The discrete resource models labor. And what's special about labor is that it can have a capacity that's greater than 1. You can have 2, 3, 4 cranes. You can have 2, 3, 4 crews, right? What's special about the disjunctive constraint is that it models the space resource, which has a unary capacity. There's only one space that all construction processes on a construction site need to use. All processes use the exact same space, and there's only one space. And what's special about the precedence constraint is that it does not model resources. You either turn it on, and you get logical schedules, or you turn it off, and you try to build a roof before the foundation. It took me 3 years to unify knowledge from other fields into the table that you see today, and to categorize the constraints this way. And it's critical to the construction method that I've built. So what is happening in construction management or construction scheduling today? Precedence in terms of constraints. Precedence constraints were introduced in 1961 by a previous professor at this department. And they have been operationalized for over 50 years using the critical path method. Really the most widely used, the founding stone of construction management today. Discrete constraints, like labor, have also been extensively researched, and they're applied to what is called modified CPM. So they modify the CPM by adding discrete constraints to it. And that has been researched. What has not really been studied a lot is the disjunctive spatial constraints. The key to understanding disjunctive spatial constraints is understanding spatial representation. There are 2 ways you can represent spaces. You can either use an area value, like 50 square meters, or you can use Cartesian coordinates. The area values don't use reference frames. They're not located anywhere. And the Cartesian coordinate systems are differentiated by whether they use a geocentric or an allocentric reference frame. A geocentric reference frame defines the location of spaces with respect to a single origin for the entire project. An example of a geocentric reference frame is north, south, east, west. These reference frames cannot be reused and automated in future projects. An allocentric reference frame defines spaces with respect to the elements of what you're trying to build. Therefore, you can reuse this in the future. So let's look at the 2 requirements that we set forth originally, which was eliminating spatial clashes while maximizing space usage. With an area value, you don't know where that area is, and so it's not possible to see if they're adjacent or on top of each other. So you can't eliminate spatial clashes and maximize space usage. With geocentric reference frames, you can partially avoid spatial clashes by not scheduling processes in the same zone, but you can't tell if work in adjacent zones interferes with each other. You can only sort of look into one zone at a time. And you can't schedule more than one process in a zone concurrently, so you can't maximize space usage. What really allows you to maximize space usage while eliminating spatial clashes is Cartesian coordinates and allocentric spatial requirements. So let's take a look at spatial schedulers today. I reviewed the 7 most widely used spatial schedulers in industry and found that these 3 use area values. These 2 use geocentric reference frames, and these 2 use allocentric reference frames. So when you look at increasing space utilization, you can see that this concept is absent from construction management today. The idea of increasing space usage has not been put forth. When you look at eliminating spatial clashes, the geocentric reference frames, as expected, partially address this. But why do the allocentric reference frames partially address this? And that's because these 2 methods are not automated schedulers. These 2 methods just detect spatial clashes. That's all they do. If you look at the ability to automatically generate multiple schedules, you can see that the theoretical gap lies because allocentric Cartesian coordinate spatial representation has not been combined with automated schedule generation. And this is what I have done. So now I will refine research question 3. How can construction managers navigate the state space by automatically generating multiple schedules? By resolving precedence, discrete, and disjunctive constraint, using construction process spatial requirement allocation methods that use allocentric and Cartesian coordinate spatial representation. So what you're trying to do for your scheduler is you want to resolve precedence discrete disjunctive constraints, and the disjunctive spatial constraints you want to use allocentric and Cartesian coordinate spatial representation. So how did I answer this research question? I created a method called the tri-constraint method. It's called the tri-constraint because it models those three constraints. I used a prototype software to run this method, and then I compared its results to those of the two most widely used scheduling methods in industry today, the critical path method and the line of balance method. The critical path method is the one that's used by most of the industry. The line of balance method is a spatial scheduler, which is why I wanted to compare my spatial scheduler to it. And we tested it on 3 construction project case studies. So what is the tri-constraint method? You start with a product model, and this is what you want to build. This is what you want to end up with and hand to the client. You convert the elements in the product model to a list of processes that you need to do, the to-do list. If you execute all of the processes in your to-do list, you will have your product model. This is actually a 19-step process that I'm not showing here. Then you apply precedence constraints, which removes processes from the to-do list that violate precedence constraints. At this point, you have a can-do list that that satisfies precedence constraints. Then you apply the disjunctive spatial constraint to get a can-do list that satisfies precedence and space. You apply the discrete resource constraint that removes the processes that violate that constraint, and you get a can-do list that satisfies precedence, space, and disjunctive. Discrete resource, sorry. At this point, you have a list of processes that you can schedule. You can schedule these to create a feasible schedule. You select the top one, and you schedule it. And that's really the core of this method. So what's new here? What have I done? And what have I taken from others? Akinci really introduced a spatial clash. And she introduced a method that detects spatial clashes. And the to-do, can-do, and doing lists were introduced by Walch, both predecessors of mine at this department. What I have done is formalize the disjunctive spatial constraint and combined it with precedence and discrete resource constraints within the context of an automated spatial scheduler. The second thing I have done is I've introduced a method that shuffles in the next simulation. The method remembers the order of the can-do list, and it changes it by moving process 2 to the top, and scheduling, instead of process 1, schedules process 2. This is really what enables varying sequence, which is what gives you the thousands of feasible scheduling solutions. This has also not been done in the context of spatial scheduler. So we now have a spatial scheduler that can generate thousands of feasible schedules. What we need, and we can measure the construction duration for each of these schedules. What we want to do is we want to measure the space usage. And if you look at space utilization metrics today, you can see that no space usage metric really allows you to measure space utilization for an entire project. Current space utilization metrics only allow you to measure space utilization for single or groups of processes. So we need a new metric. And I did this by introducing the average space utilization factor. The average space utilization factor uses the space utilization factor, which is simply the ratio of the total required space, so the ratio of these colored rectangles, divided by the total available space, which is the black rectangles, at each time interval in the project. You simply average the SUFs to get the average space utilization factor, the ASUF. And this is a metric that gives you space utilization for an entire project.
Just a quick clarification. Is that the space that has all the prerequisite activities performed for these activities to take place, or just space in the building somewhere that may or may not be ready for these tasks to be done?
So this is the entire space. Yes. Yeah, ask me that. This is a good question. So this average space utilization factor is automatically calculated with the tri-constraint method. The blue line represents the boundary of your construction site. And you can see that 0% of the space is being used in this image. Here you can see that 100% of the space is being used for construction. 83 and 48%. So when you average this for the entire project, you get 72%, which is your average space utilization factor. The line of balance method to calculate space usage with it is more complicated because it doesn't do that automatically. What you need to do here, in the line of balance method, construction processes are in zone 1, 2, and 3, and this is day 1, day 2, 3, 4, 5, etc. So you can see that it's in zone 1 and then moves to zone 2. You need to look at each day individually and then see that work is occurring in zone 1, work is occurring in zone 2, and work is occurring in zone 3, and you write that down. You do that for every single day. Another example is for this day. You can see that work is occurring in zone 1, nothing is occurring in zone 2, work is occurring in zone 3. You do that for the entire project, average the numbers out, and you get your average space usage, space utilization factor. So what we want to do is we want to compare the tri-constraint method to the CPM line of balance schedules. To do that, we'll run 10,000 TCM simulations, we'll create a line of balance schedule, we'll create a CPM schedule, and then we'll compare the space utilizations and construction durations for these three methods. The dependent variable of this experiment is the construction scheduling method. So whether you select TCM line of balance or CPM. And you want to study the effect of these scheduling methods on construction duration and space utilization. And then we want to see the relationship between these two, construction duration and space usage. That's what we really set out to do. The problem is that labor capacity also affects construction duration and space utilization. Therefore, to eliminate the effects of this variable, we remove it by assuming infinite discrete labor resources for this experiment. So we'll assume that you have as many people as you need at any time. So what does the tri-constraint method output look like? What's the end result? Well, you can see that it shows you which construction processes occur where at what time. This is a visual that's really overlaid on top of a construction site. And now I'll show you the fastest of 10,000 runs. TCM created 10,000 sequencing possibilities and selected the fastest. You can see that it shows you a 4D model of which processes need to occur where at what time, while automatically varying sequence. So what are the construction duration results between these three scheduling methods? When you compare the line of balance method to the tri-constraint method, the new method that I developed, you'll see that the tri-constraint method, or the line of balance method, has durations on average 45% longer than TCM. This is for two reasons. The first is that the line of balance method uses these large chunks of space that's pretty inefficient compared to the smaller exact spatial requirements of TCM. The second reason is that the line of balance method only creates one schedule, whereas the tri-constraint method looks at 10,000 possibilities. So now let's look at the critical path method, the most widely used method in industry today. You can see that the critical path method durations are half as short than as those of the TCM method. So you might be thinking, well, CPM, the critical path method, is the method I want to use. Well, the reason that you get these short durations is simply put that if you assume that you have infinite resources, CPM schedules everything in the same space at the same time, which is not feasible. This is the method that's used by the industry today, the most widely used method. It does not model space. It does not let you understand how to move, cruise, or work through space. So let's look at the ASOF results, the average space utilization factor. Well, you see that the line of balance has a much higher number than the TCM method. So even though it has longer durations. So this is incorrect. The reason being is that the TCM method uses exact spatial requirements, as you can see here, whereas the line of balance uses these large chunks. So you're under the illusion that you're using a lot of space, whereas in fact, you're not. You're inefficiently using your resource of space with line of balance. So even though it's higher space usage, the duration is longer. So what we set out to do was find the link between the average space utilization factor and the construction duration. The easiest way to do that is to use the 10,000 schedules that we have from TCM. For each one of these schedules, we have the construction duration and the average space utilization factor. We have these values. So something really interesting happens when you multiply these two numbers together for any schedule. They give a constant. This is a remarkable result because it shows you that space utilization is inversely correlated to construction duration. And it's actually a mathematical formula that's given by this. The average space utilization factor multiplied by the construction duration is the sum of all the individual processes times the area of the individual processes times the duration of the processes, that whole thing divided by the area of the construction site. Just to give an example, the ASIF times the construction duration, which is a constant, is area of process A times duration of process A plus area of process B times duration of process B plus area of process N times duration of process N. This whole thing is summed and divided by the total area. This number, the constant that you're calculating, does not need you to create a schedule. It's really easy to calculate. All you do is multiply the areas times the durations and divide it by the total area of the construction site. To conceptualize the average space utilization factor, I'll show a graphical way that demonstrates it. Imagine you have a process A with a duration of 1 hour that needs half the site, or 54 square meters in this case. What you need to do is extrude the area by the duration of the process. So this is 54 square meters, and this is 1 hour. If you do that for all your processes for this construction project, well, each one of these blocks is a construction process. And that's what you end up with. So what is the construction process? I mean, if this is your processes, how do you build, or where's the time dimension? Well, you can see that with this graph over here. You start the project, and at time 2, you're working on the green and the blue process. At time 7, you're working on the light blue process. And you can see that really you're conceptualizing the black area at the bottom is your construction site, and you're really conceptualizing construction as throughput via the capacity of the construction site's area. So why is ASIF times construction duration a constant, since that's what that equation gives us? The reason that it's a constant can be seen by taking two sequences. These are two actual sequences of the same project. In sequence X, you finish the project in 12 hours. In sequence Y, you finish in 9. You finish faster. Well, so what's the average space utilization factor? Well, the average utilization of space is a column of uniform cross-sectional area. The average area of the colored blocks equals the white block in sequence X. And in sequence Y, the average area of the colored blocks equals this column. The volume of those blocks is constant. And that's really what that constant is. It's just the volume of these blocks. So, of course, if you have a longer column, the white area is the percentage of the total area that's being used. You can see that an average space usage of 43.8%. So when 43.8% of the total area of the construction site, of the black, is being used for production, your duration is 12 hours. If you want to decrease the duration, well, you've got to increase the area for a fixed volume. And you can see that here. I've used the same width, but you can see that you're using just that little bit more average space. From 43 to 58 reduces duration from 12 to 9. And that's this equation here. This equation gives you the operational efficiency frontier. You do not need to calculate, you do not need to schedule to obtain this equation. So let's look at it for a little bit. What happens when ASIF is 100%? What happens when you use 100% of available space throughout the entire construction project? Well, 1 times the construction duration is a constant. So the height of that column, if you use 100% of available space for construction, is equal to the fastest that this construction project can be built if you do not allow spatial overlaps. It's kind of the same as if you took these colored blocks and converted them to water, an incompressible liquid. They would fill a column of this height. You can also mathematically derive this equation, which I will not get into here. So what we want to do is understand the trade-off between space utilization and construction duration. To do that, I've shown you how to basically calculate this operational efficiency frontier, and I'll show you how it works next. And what we really want to understand is which of these variables can you use to navigate along the frontier, and which of these variables can you use to manipulate the frontier to new locations. I've shown you the operational efficiency frontier, the equation for that. Construction duration times ASIF, average space utilization factor, equals a constant. What I'll do next is I'll show you the effect that construction sequence and construction scheduling method have. What we'll do is we'll use 3 case studies, the 3 case studies that I think I introduced earlier. We'll take 3 construction scheduling methods, which is a critical path method, the tri-constraint method that I've introduced, and the line of balance method. We'll basically generate 10,000 schedules with the TCM method, and we have its CD, construction duration, and average space utilization coordinates, so we'll plot those onto 3 graphs for the 3 projects. Next, we'll create a schedule for the line of balance method and plot it there. And then we'll calculate the operational efficiency frontier for these 3 methods and plot it on the same graph. So what do the results look like? We'll start with the bio-e-chemie project. First, we'll plot 10,000 schedules using the TCM method. You can see that this really shows you the effect of varying construction sequence. What is construction sequence? It really gives you these dots. Then, a human scheduler will create the line of balance method and calculate manually, and this is key, manually calculate the average space utilization factor, like I showed you how. Then you create a CPM schedule. When you have infinite resources, a CPM schedule gives you 1 duration. For that 1 duration, CPM does not use space. So we basically drew a line that represents 0 to 100% space usage. That's the CPM method. Now, we need to use this equation. So for each of these projects, we took the area times duration of each process, summed it, divided by total area, and we got an asymptotic curve. We drew it for the line of balance method. That was the first thing we did. Notice that the manual calculation lies actually within 3% of the value predicted by this theoretical equation. Then we plotted the operational efficiency frontier for these 1,000 points. You can see the effect that construction scheduling method, changing from line of balance to TCM, gives you a much more efficient efficiency frontier. And you can see that the durations are shorter, somewhere around 72 versus somewhere around 130. So why is this the case? Where's the inefficiency coming from? And this is comparing not 2 schedules, but 2 scheduling methods. The inefficiency comes from the fact that the line of balance method uses these large chunks of space. It gets the same result just using more resources, while a TCM uses the exact spatial requirements. So just to contextualize this, you can see that the results you're getting theoretically around the maximum that you can get with TCM around 60%, with the line of balance somewhere around 90%. So I'd like you to take your attention, and if you remember, I measured that the industry today uses an average of 3% of space usage. So if you extruded this graph all the way to the X over there, that's where current construction industry practice is today, the red X outside. As you can see that there's a significant potential to improve this process. So what I've demonstrated here is how you can navigate the state space with construction sequence. And I've also shown how you can manipulate the state space with construction scheduling method. For the 3 case studies, next we'll look at the men's fashion and the accessorized projects. We follow the same procedure, and you can see that you get really very similar graphs. The TCM method is more efficient than the line of balance method in allocating space. And the CPM method, even though the tri-constraint method is designed to, at every point in the simulation, use all available space. It's a greedy-first algorithm that literally does not move forward in time until you run out of space. It just schedules everything it can at any given time, and it tries 10,000 ways to do it. You can see that you don't get close, nowhere close to the durations given by CPM. CPM is in the set state space of infeasible solutions for this method. And it really is infeasible because it's scheduling everything in the same space at the same time. So what I've shown is the operational efficiency frontier, how to navigate the state space with construction sequence and manipulate it with construction scheduling method. Next, I'll show you the effective labor capacity. So if you have various numbers of people. So we'll take the bioengineering chemical engineering project. And what we'll do is we'll now set a limited number of labor. First, we have 1 crew of each type. So 1 carpenter crew, 1 painting crew, 1 concrete crew, etc. You can see that 1,000 simulations give you durations of 260 on average. This is infinite crews. And you can see that the fastest you can build around 72. This is 1 crew. So what if you have 2 crews available? That's 1,000 runs. 3 crews, 4 crews, 5 crews, and the red dots are infinite crews. You can see how you can navigate the state space with a discrete resource labor capacity variable. So I've shown the labor capacity. Next, I will show you the effect of schedule execution, more specifically, delays. Consider an example project of 8 construction processes and 4 possible sequences. This is the Gantt chart. You can see that the colors are the same, representing the individual processes. Sequence, for the same construction project, you have sequence AE, AG, CE, and CG, which gives you durations of 9 hours, 11 hours, 10 hours, and 12 hours. You use this equation to calculate the efficiency frontier. You multiply the area times the duration for each process. You get the sum product, which is 570. And then you divide that 570 by the total area of the construction site, which in this case is 108 square meters. That gives you a constant of 5.26. This is an asymptotic function. Yx equals k. So you plot this along with the 4 sequencing options that you have. So at this point, you're on the efficiency frontier. There's no delays. You select sequence CG. Note that this is the slowest sequence available to you. But maybe you select it because it's the cheapest. So the construction project starts, and as often as anyone in construction knows, one of the processes is delayed. So if you recall, what we did originally is we multiplied these two, the area times the duration of these, to get 570, and we divided 570 by the total area to get the constant 5.26. Process A is delayed from 1 hour to 3 hours, which changes the area duration to 162, which changes the sum product to 679, which in turn, the same area, changes the constant to 6.26. For an asymptotic curve, increasing the constant moves the curves to the right. So let's plot this. Follow the sequence that we selected, which is CG. Now, with the new frontier, you can see that with the delay causes CG and other sequences on that frontier to move to the right, to what was originally an inefficient set of solutions. These solutions are now no longer available to the construction team. What you can then decide is to mitigate this delay. You select sequence CE. You sequence from CG to CE, thereby mitigating this delay and finishing the project at 12 hours again. So this shows you how a construction delay manipulates the state space, and also how you can navigate the state space by resequencing. So we've seen schedule execution and delay. The contributions that I presented today is the operational efficiency frontier method, which is specifically a method to visualize the scheduling state space by demarcating the sets of infeasible, inefficient, and efficient solutions. That's research question 1. You can use that method specific variables to move the operational efficiency frontier. And I've demonstrated how you can do that with schedule execution, specifically delays, and construction scheduling method, which is research question 2. The second contribution I presented is the tri-constraint method, a method to navigate the state space by automatically generating multiple schedules. And I've shown how you can vary construction sequence and discrete resource capacity to that end. More specifically, within the construction scheduling method, my contributions are that I've combined precedence and discrete constraints with disjunctive spatial constraints that use Cartesian coordinate and allocentric spatial representation. The second sub-contribution for the automated scheduler is I've introduced a method that allows you to vary sequence by shuffling construction processes in the can-do list. This has also not been done. So what are the practical implications? Well, first of all, I've placed an emphasis on considering space as a resource. You can really start thinking of throughput via construction sites' areas capacity. Space has special properties. It is unary, there's only one space available, and at the same time it is free. That's why coordinating it is critical to construction scheduling. Another implication is that with this method, you can generate thousands of feasible schedules. And you can visualize, navigate, and manipulate the state space. Simply put, these implications will will make it faster and cheaper to build construction projects. So the future work, well, I've introduced the operational efficiency frontier, an automated scheduling method, and I've shown how these variables can be used to navigate and manipulate the state space. So instead of, what we're doing today is randomly varying sequence. So instead of that, you'd want to develop heuristics to generate not a random 10,000 set of schedules, but you want to generate the right, quote unquote, set of schedules. You want a more effective way of navigation. Next, you want to rank the can-do list, so not shuffle it, but rank it, for example, by location, which will enable you to do things such as workflow, which is not currently done in the method. So these are just 4 variables I've introduced. But really, what you want to establish is what is the effect of other variables? Do they navigate or manipulate the state space? And really, from that equation, if you remember, any variable that affects the duration or the area of construction processes will change the location of the operational efficiency frontier. And finally, I'd like to test the generality of the operational efficiency frontier in other fields. For example, can it be used in logistics? So the PhD journey is a strange journey because it is one of the few journeys in life that you must tread alone. At the same time, it is impossible without the help of so many. I would like to start by thanking the institutional support of SciFi, the Charles Level Fellowship, and Slavenberg, construction in the Netherlands. Where would one be without their friends? And they're really what pulled me through the low points during this research. So thank you. I have been, one of the great blessings of this, this endeavor was to be surrounded by colleagues of such caliber who served as examples which I have aspired to and learned from. I have to thank the research assistants, first and foremost, for putting up with me during the endless hours of debugging, simulating, discussing, brainstorming, and researching. I have to thank special people from the industry whose belief in an innovative construction future enabled this research, and they really helped us validate and crystallize some of these problems. Thank you. Of course, a big thank you to Michael Lepek, Ram Rajagopal, and Warren Hausman, who are on my committee. In institutions such as this one, it is truly difficult to find people that will simply help. A special thanks to two people that couldn't be here today with us. Robert Carlson was an original member of my committee and was critical in formulating the research in its early stages. And Sylvester Slavenberg was a mentor for the past 5 years. Finally, a very special thanks to two very special people. John Kuntz, who really advised me and guided me and helped me from my first day here at Stanford. He's the one that told me to pursue this topic. And I once asked John, I said, John, I think not only do you know what I'm going to ask you next, but you know when I'm going to ask you. And he absolutely assured me that that was correct. And finally, I need to thank the man who's ultimately responsible for this, my principal advisor, Martin Fisher. I don't really know why he accepted me 6 years ago to this program, but one thing that Martin has taught me over the years is to be specific. And so I'll thank him for two specific things. If Martin had told me what to research, I wouldn't have developed a new way to schedule construction projects. And it is really challenging to give someone the freedom to develop and at the same time come in at the critical junctures and nudge them in the right directions. 6 years down the line, when I look at it in retrospect, the paper of Echeverry, which led to the understanding of the constraints, the artificial intelligence class that I took, the WALK paper, which was the to-do, can-do, and doing list, Fondal's paper, which allowed me to understand that CPM assumes infinite resources, were actually all Martin's suggestions. The second thing I want to thank Martin for is his consistent rejection of my quality throughout the years, which has forced me to continually improve. In doing so, Martin really believed in me when I didn't believe in myself. This work represents a departure from current construction practice, and perhaps even philosophy, of generating a single schedule by demonstrating a method to visualize, manipulate, and navigate the construction scheduling state space. As Einstein said, space and time are modes by which we think and not conditions in which we live. Current construction industry views space and time as dimensions in which we work. This research presents them as dimensions with which we can think. Thank you.
We have time for some questions from the general group.
Professor?
So I was trying to, first of all, congratulations for a very nice piece of work. This takes construction scheduling closer to some of the kind of parametric design that people like Boris and others, later others, have brought into scientific game. So I was frankly a little irritated by your comparisons with CPM, which was kind of a setup. Nobody in the real world, CPM schedules don't design themselves. They're designed by humans who take into account constraints other than the logical, physical constraints. They understand that they can't put 50 people in one room, so they show them in a sequence, but it's arbitrary, and they can't possibly explore all of them. So I think you ought to tone down your critique of CPM by making it more realistic, not to take a single CPM schedule that any experienced person who knows completely unrealistic and use that as kind of a strong man to show how to make your system. The system is great, but CPM isn't that bad when it's done by an experienced person. So that was frankly a little irritating. In any case, the other thing is that the optimization problem is not a project optimization problem. Most buildings are built by multiple firms. And each subcontractor is optimizing not just its work on this project, but its work across multiple projects. So one of your optimum schedules along the efficiency frontier might require a subcontractor to do something that's very non-optimal for them, especially across this project and 5 other projects. And part of the reason is 3% of space utilized is that, plus general contractors historically don't have enough coordination capacity to manage something like this in real time that things are changing. With 5 guys in a trailer supervising 500 people in a building that they can't even see from the other side of the lights and YouTube building. And unless they have much more coordination capacity on the site, this would not be feasible. If things were changing, then they would know exactly what is going on. So I think those, again, are ways you can temper the contribution and detect emissions. But it's a very nice contribution.
Thank you. If I can, I completely agree with both points. With the first point, though, I'd just like to point out that I spent a lot of time thinking, what you said is that with a CPM schedule, a human will not do this.
No, they won't, but they won't produce completely unrealistic schedule. They'll just produce one schedule, two maybe, if they look at a couple of alternatives.
But what I want to study is really the method. So not a human scheduler. So what I want to do is algorithmize it. So that's, I completely agree, is that a human scheduler will not do this, but that's what I'm trying to say, is that what I want to do is study the method by itself.
And that's a beautiful contribution. But setting up a sort of a horse race between noise versus CPM versus line of balance, where the line of balance is using a much coarser geometric representation of the whole floor of the building, which, by the way, is what a subcontractor might consider to be efficient, versus working in one room and then coming back 3 days later to work in another room. Again, it's not a fair comparison. So we'll make the others look too bad in this presentation again in the way that I personally find it. So I'll say.
Mark?
This sort of relates to what Ray was saying. I sort of see that you're optimizing sort of the space utilization within the project, but not trying to figure out how to optimize the resource utilization. In particular, if you have enough people to fill all the spaces at any given point in time, what do those people do when they can no longer work in those areas? Do they sit around and wait for the next subject? I mean, how do you really bring in the sort of resource usage optimization using this algorithm using like that?
What you're doing is you're calculating the number of idle days for each one of these schedules. So this is really calculating costs. So you're correct. What in the 45 minutes, this work really doesn't represent a large portion of everything I've looked at. But the question is, how do you look at idle days, coordination, etc. So the key is you need to calculate. You can start. What I was optimizing for was duration, because of the fact that there's that mathematical relationship. But you want to optimize for idle days and ease of building. This also, by the way, ties into what Professor Levitt was saying, which really a very critical part of the research was the definition of the level of detail. So basically what I'm doing is I'm looking at the scope, the amount of the quantity of a product that you're working on. And the reason that I'm looking at single elements is because that's what BIM models are. They're groups of elements. But to answer the question, what you want to do is you want to aggregate these elements to create, because at this point in time, that's what Professor Levitt was saying, you can't give schedules that are that detailed. So you want to aggregate these elements to create schedules that humans can use. And that's really, I think, in construction, I believe the solution is that you need to create data or information at a coarse level of detail, increase it automatically, simulate at that level, and then aggregate it again.
And that would be a little like critique about subcontractors having to have a relatively efficient use of the job sites, given all the other job sites they have to do.
Yes. Yeah, absolutely. Maurice?
What's the cost?
Oh, the cost? The cost is fairly simple. Once you have the schedules, you just look at which crews are working on which day. And if somebody shows up to work, even works for 2 hours, you pay for a full day. You'll see here that, interestingly, the fastest schedules are a little more expensive than the cheapest, which kind of makes sense. Henning?
Have you looked at the constraints proposed by the Toyota production method as maybe incorporating into your algorithm? So
constraints such as?
Let me look at available resources like steel and so product resource availability and weather delays. I feel like those could be modeled as variables, including algorithm.
The critical thing in this research is the level of detail. Excuse me. What you're saying is other constraints. So other constraint types, there's two parts to this question. So within the types of constraints that I've shown, what other subcategories are there? So that's answered here. So subcategories are, you can see the product, the method, the organization, and the actual process. So the organization you also have, that can be equipment, and it can be material. So those are basically discrete resources as well. One of them is a stack, because you put the crew back in the stack, material gets used. And the other question was, the constraints themselves. So when you look at Echeverry's paper, which really gives you a list of, I think there's 18 construction scheduling constraints, you can actually categorize all of those by precedence, disjunctive, and discrete. So to answer the question, at this point in time, I am not aware of a construction constraint that you cannot model using these three types. But I'm certain that it exists. You know, I mean, I think fundamentally what you want to do is you want to, I've really been interested in out of these three, can you make one? So I've shown from Echeverry's work how each one of the 18 that Echeverry presents is actually one of these three, but can you then actually create like one type of constraint? I'm not sure. Forrest?
A lot of your work focuses on space constraint, and I know you had glossed over what is the space that each activity by method actually uses. How do you propose solving that?
So this was the first hurdle, and this is an excellent question. So this really, when I started the research, the question was, well, how do you know how much space you need, right? So interestingly enough, this seemed like a really big problem in the beginning, but there's several things that really sort of were like, you know, these kind of light bulb moments. The first was that construction managers actually had that information in their head. So I remember when I was sitting with Eric and I had 50 copies of the layout, and we went through the processes, you know, it was like 25 minutes for him to say, installing this, he just draw little boxes. But he was like installing rebar, steel, this, that, you know, I mean, it's literally like really fast. So then the question is, okay, so how important is it that you've got the actual, what's your error, right? Does it need to be within a millimeter, within a centimeter, within 5, within 20, within 30? So there's several things you can do about that as well. I've looked at allowing spatial overlaps. So you can allow like 10%, 20% overlaps. What's the effect of an overlap on the productivity and how? I didn't show this here. And the second thing I ran like 3 years ago was a sensitivity analysis because of specifically that question. And when you vary the spaces by 10, 20%, it doesn't, when you're using, not when you're using, if you vary the space by 20% here, then these two will overlap. That changes everything unless you're allowing overlaps. When you're varying it by 10, 20% here, doesn't like really, there is a change in the durations, but it's not huge. So, Lev?
So most construction managers have multiple projects in their portfolio at once. How does the multiple project scenario change the efficiency?
Right. This is also, sort of similar to what Professor Levitt was saying. I focused on one project. So what you need to do, I don't see any reason why I can't load 5 projects into the system and have it run. How do the projects interrelate? I could give you a really long-winded answer, but the simple one is I don't currently know. That's one of the other variables you'd want to look at. Forrest?
I thought it was really interesting in terms of looking at scheduling as a sort of spatial utilization problem. I do wonder, when you're presenting it as a trade-off between duration and space utilization, I wonder why you've chosen that as like a trade-off. Would someone actually suggest or pick one with a lower space utilization and a higher duration, or what makes that trade-off interesting?
Well, to me, what made it interesting was that I really remember. I really remember in Afghanistan when I was walking, Henry would show up and I'd walk out. And many times I'm like, it doesn't look like we're doing anything. This guy's gonna like ding me for this. And then years later, in the middle of a meeting, when the subcontractors I cannot work any faster. That was what they were saying. We can't work any faster. We can't. And then you look outside and you see all this empty space. When you drive around and look at, all the construction projects I've been on, look like that. They're just large expanses of empty space. I'm looking for that picture that I currently can't seem to. Oh, there we go. And this is a typical construction site.
René, could you clarify, you showed the cost of idle time. Why couldn't you just put that into your equation as a third dimension, where you could then optimize, you could have a 3D, for example?
Completely.
Because then you come much closer to the way the subcontractors think about the job. If you can minimize their idle time on the job, they love it. That's just good.
Completely. There's two reasons. The first one is that when you look at idle time, it's a stepped function. So I don't think, I don't know, but I think you might be able to find heuristics for it, like a limit, but which you can't exceed. But I don't think you can find like a mathematical equation that will predict it.
If you look at the largest number of subcontractors you have on the job at any one time,
Yes.
and you see that they were all there the whole time, and idle time was anything not being used up to 50 minutes, that would give you, I think, a realistic measure for subcontractors' efficiency.
This question is exactly why I use the words navigate, manipulate, and visualize. Because what I'm trying to say with this is, look, these are four variables that affect two metrics. That's nice, but this three-dimension, what is the operational efficiency plane, right? Or curve, right? That's a.
Because some clients would be very happy to pay for idle time to finish a job fast. Intel is out in the semiconductor fab that's worth millions of dollars an hour. They'll be happy to pay for idle time. Anyone who puts a big room together is paying for idle time to improve automation. People are willing to pay for that.
I'm pulling something up.
One more.
Eric?
Yeah, I just wanted to address the subcontractor, the various with multiple projects. I mean, and I'm very interested in what René has to say because I wrote the CPM for BioE. But I mean, we can negotiate that up front. We do all the time. Whether you owe me 3 crews, 5 crews, or 10 crews, and your other projects are really not my concern for my specific project. That's kind of overcome. The thing that I found, which was similar to when I was working with you, we were at the same time trying to do 4-dimension with our 3D model and our CPM, and that we found that with a building like BioE that had such unique spaces and very few repetitive spaces, that the task of identifying all the items within the 3D model was pretty arduous. I mean, it would have taken my 15,000 activity schedule and made it 150,000 activities to get the 3D model, the 4D model to work properly. And I'm just curious, with your method, I mean, are we sort of in the same position where we have to identify such detail and a minutia that it becomes an arduous task up front?
So this is, what you're talking about is this step here. I'll answer this question and then we're out of time. The idea is you want to create information at a coarse level of detail, allow the software to simulate at a high, and then aggregate up. So you're exactly correct. If you create information for every one of these elements, a human couldn't schedule it. So I'm actually researching, it's a 19-step process that I don't know if I'll be able to find it. It's in the, oh, there we go. So these are 8 of those steps. You start with a, God, that's such poor resolution. You start with an element, you choose a method, you get the resources, you find the areas, you modify the production rates, and that gives you the construction operations. The key is how do you then get the precedent, how do you do this? So you want to automatically generate the input file from the model, right?
So I think we'll close the public area. Thank you very much.